We're going to be in chapter 4 today. We find ourselves in another situation where we don't have enough information for 2 full classes, but too much for 1. So what we're going to do today is we're going to talk about photons and what a photon is. We're going to talk about velocity and amplitude, and we're going to talk about frequency and wavelength, spend a little bit of time on that. We're going to talk about the wave equation. We'll get into the electromagnetic spectrum and talk about how the different, we'll use the different portions of the electromagnetic spectrum in imaging. And then we'll touch on ionizing radiation again. We've kind of done that to death already this semester. It's just any kind of radiation with high enough energy can knock out an orbital electron. So we'll talk about all of that, and we'll stop it with waves and particles because it gets a little bit funky in waves and particles. And I'll try to find a good video on YouTube that'll help to explain the duality of waves and particles in the electromagnetic spectrum and help to hopefully help you to understand that a little bit better. But we'll just pick up with photon. And so this chapter is all about electromagnetic energy, which is what we've been leading up to this point. That's a little darker than what I want. I've got a red one over here, so we'll use it. So yeah, it's red-ish. All right, so the electromagnetic spectrum is a continuum of electromagnetic energies from low to high energy. So when we're talking about electromagnetic energy, we're talking about things like light, things that behave like light in a lot of ways. There's going to be some differences in the energy levels and how they behave and what we can do with each one of those things, and you know, how we can observe them in their energy levels. But I just want to get started by having you look at the chart on page 58, and I think we've looked at it a time or two. But that is representative of the electromagnetic spectrum from low energy to high energy. High energy is at the top of that diagram, low energy is at the bottom of it. So we're going to talk about energy, frequency, and wavelength, all 3, in context of the electromagnetic spectrum and different types of electromagnetic energy. So we'll go back to the Greeks. There's a word, it's photon, and we've used that here in class. Whenever we make an X-ray, be it a characteristic or a Brem's X-ray, we call that individual X-ray a X-ray photon. Right, it's photon. So a photon is kind of like a single piece of electromagnetic energy. So if we go back to the last chapter, we said a single piece of something is what? Of matter is a atom. It's an atom, right? So there's a correlation there. You know, the Greek word for photon is kind of like a single piece or an atom of light, single piece of electromagnetic energy. They didn't know what electromagnetic energy was, but they knew what light was, in the same way that as soon as you are old enough that your eyes can focus, you can utilize light. You might not know what it is, but you can utilize light as what enables us to see things. So we're going to talk about how light works, and we're going to talk about the difference between light, radio frequency, and X-rays, gamma rays, and things like that. So a photon is a quantum, a quantity, a portion of all of those are really kind of one and the same. A quantum of light, a photon of light, an atom of light is essentially what we're talking about there. A single piece of electromagnetic energy. So regardless of what the energy level is that we're talking about, electromagnetic energy all behaves in specific ways. First off, it travels at the speed of light. All has the same velocity. Velocity means speed, right? So it all travels at the speed of light. Einstein called speed of light constant, and it is constant in a vacuum. Vacuum of space, it's always going to travel at the same speed, and it's really, really fast, right? And what we mean by being constant in that context is that you can't speed it up or slow it down. Okay, so if it's in a vacuum, you know, we got satellites that are buzzing around the planet, right? And if we put a flashlight on front of the satellite, then the light that's coming off that flashlight, it's not gonna go satellite speed plus speed of light, it's gonna go speed of light, okay? But light does change whenever it enters a medium, all right? So speed of light here at sea level is not gonna be exactly the same as what it is in vacuum, because we've got, you know, an atmosphere. So it's got to go through molecules, got to bounce off molecules or hit molecules and then be re-emitted. So it's not going to travel at exactly the same speed. It's still going to be really, really, really fast though. So the guy who described the characteristics of electromagnetic radiation, electromagnetic energy, was a guy named James Clerk Maxwell. It's just memorization. This is top of page 54 in the right-hand column. And he described that in the late 19th century. And he said that it had certain characteristics. It had a constant velocity. Really, Einstein, you know, defined that. Constant velocity. And it traveled in wave forms. All right, so what's a wave? You go to the beach and what do you see? You know, yeah, it's just, you know, the waves, right? Yeah, it's current going through the water, you know, caused by wind, caused by the shifting tides of the moon, gravitational pull of the moon and all that. So it travels in wave forms. And so with the wave, let's say you go to the beach and it's particularly windy and it's been windy for a few days. What do you see different in the waves? They're choppy, yeah, they'll knock you down, right? So the waves will have different heights. You know, some days you go, we usually go to the beach in between the summer and fall semester. This last time we went, there were surfers all over the place. So we go to Florida, you don't see surfers quite as much in Florida as what you do in California, but there were surfers all over the place because the waves were kind of high. It beat you around a little bit. All right, so a little bit higher this time than in previous years. Saw a lot of surfers. So we've got a height, okay, and we call that height amplitude. Okay, so we've got velocity. We already talked about velocity. Velocity of light is
constant.
What's that?
Constant in vacuum.
Constant in a vacuum, and we call it the
Speed of
speed of
light.
light, right? Speed of light. So light travels at the speed of light, right? So X-rays travel at the speed of light. Radio frequency, also on the electromagnetic spectrum, travels at speed of light, right? If you happen to have the DeAngelis, I don't know that this question is still in there. It was in the DeAngelis in a lot of different editions. Well, it hadn't had a lot of different editions, but it was in previous editions. And there was a question in there that says the primary difference between sound and visible light is frequency and wavelength. And that is completely inaccurate. Okay, sound is a totally different type of energy. Sound requires vibration of molecules. The reason you're hearing my voice is because, you know, you got the vibration of molecules that mess with the, you know, the organs of hearing in your ears, and you receive that vibration and your brain detects it, right? So that's totally different. Okay, so that question, you read that question, just, you know, throw it away. So sound does not behave like light, and it's not the same type of energy. We still use sound in ultrasound for imaging, and the image that's coming out of the computer, okay, yeah, we've got electromagnetic radiation there, but creation of that image is through sound waves and not through electromagnetic radiation. Okay, so if you see if that's still in the DeAngelis, just understand it should have never made it into the DeAngelis, and it should come out, you know, and future editions. So anyway, we've got a velocity. Velocity is constant in a medium or in space or, you know, in a vacuum. It's, you know, the light here, the light that's traveling from the light bulbs to me is no different than the light that's traveling from the light bulbs to you. You know, it's still constant. It's just not at the accepted 186 miles a second, right? It's just a little bit slower. That 186,000 miles per second is in the vacuum of space. So velocity, speed, amplitude is the height of the wave. And the height of the wave represents, kind of like at the beach, the intensity. You know, you walk out and you're in this deep of water and, you know, you're catching waves that are 2 feet over your head. Somebody's, you know, you come back in, somebody says, you know, how's the water? How are the waves? They're kind of intense, you know? Okay, so think of the height of the wave as the intensity of the wave. Okay, so then what we have is frequency and wavelength. All right, so individually, when you think of frequency, what are you thinking of? How often something happens, right? So we use frequency in a lot of different contexts. You know, if we're taking a history on a patient, we're doing IVP, which we don't do a whole lot of anymore, but maybe you go into CT or whatever, and you'll take a history on a patient, and they say, I have increased frequency. What that means is they got to go to the bathroom more often. So do they have a prostate issue? Do they have a kidney issue? What's going on with the patient, right? Frequency, how often something happens. Wavelength, what does that sound like? These two are not complicated, right? It's just the length of the wave. So what Maxwell determined was that electromagnetic energy has specific amplitude, intensity, and it travels in what we refer to as sinusoidal variation. So it goes up and down and up and down. And we see sinusoidal variations. We're going to talk about those later in the semester in context of electricity. So we have two different types of electricity. We have direct current. Direct current is what you get from batteries. It just comes out in one direction, doesn't change. Alternating current is what you're more familiar with, even if you're not, you know, even if you don't see it and recognize it. That's what, if you plug your, you know, computer or whatever into a wall socket, that's what comes into your house, is alternating current. So alternating current goes in one direction, followed by the other direction, but it also travels in a sinusoidal wave, so that, you know, if you were to take something, so if I can find something that will do this for me. Here we go. If y'all haven't noticed, I kind of fly by the seat of my pants, right? So if I were to take something and swing it like this, back and forth, okay, where is it probably traveling the fastest? At the end or right down at the bottom? At the bottom, right. So, you know, I bring it all the way up like this, and it's stationary for just a split second. But when I drop it, it accelerates, right? It accelerates until it gets to its fastest speed down here, and then it starts to slow down until it comes to a stop, right? So the same thing is going on with your sinusoidal variations, be they with electricity. And with electricity, we've actually got a difference in speed of the electrons and the power of the electrons. With electromagnetic radiation, it's the intensity. Okay, it's most intense here, it's least intense down there. The amplitude is measured from the you know, halfway between both peak and valley. So your amplitude is measured here. So the velocity, it's always the same. We'll get back to that in a second. Frequency is how often we get these things. So with electricity, what we get is 60 hertz. Okay, so frequency is measured in hertz. 60 hertz. That means 60 cycles per second. A cycle would be where we start the wave and where we end the wave. So one wave goes in one direction, followed by the opposite direction, and it comes back to this neutral point, 0 point, resting spot, whatever you want to call it, doesn't really matter. But that is one wave. So this is the length of one wave. That would be probably, in this case, I don't know, 5 inches. Okay? So 5 inches, the frequency would be basically how fast that's going through a wave, and we're going to get there here in just a second. So amplitude is the height of the wave halfway in between this point, well, this point and this point. So it's from that spot to here is the amplitude. The wavelength is from the exact same spot on 2 adjacent waves. So we've got the start of the wave here, the end of the wave there, but the end of the wave is continuous with the start of the next wave, right? So our wavelength goes from here to here. Okay, so it's amplitude and wavelength and velocity. Velocity is constant at the speed of light, right? So that's those three. Now, looking back at your diagram on page 58, what do you notice? What do you notice in wavelength?
Really short together at the top and then we get longer.
Exactly. They're really short at the top and really long at the bottom compared to the top, right? So what I did when I was in school and we were going through this, we actually had a physicist that was teaching the class. And he was a great guy. He ran the planetarium, nicest guy you ever wanted to meet, but he just didn't know a whole lot about imaging physics. Before that, we had the guy that was the Bushong before Bushong. He actually taught here at TJC, and he was a little intense. I think Mindy might have had him, so you might talk to Mindy about him. If she didn't have him, the class before her had him. He'd ask a question. If you gave the wrong answer, he'd throw an eraser at you. He was old school, right? So, what was the name? Watkins, I think. No, that was my history instructor. I forget what my physics instructor's name was. But we actually calculated a radio frequency wavelength, and it was for a radio station out of Dallas. I don't even know if it's, I don't know what kind of music they play, but it was what we called at the time Q102. We actually calculated the length of the wave for that frequency, for that particular radio station, and it was in yards long. It was like, I don't remember if it was 3 yards, close to 10 feet, or if it was 10 yards, like 30 feet long, but that was the length of the wave. So you look back at your diagram on page 58, where does radio frequency fall on that?
The very bottom.
At the very bottom, so it's long wavelength, right? So compare that to X-ray, and what do you see? X-rays and gamma rays. Comparatively speaking, X-rays and gamma rays are very, very, very short, right? So let's draw this out just a little bit more. I'm going to get rid of some of the traffic here so we can just kind of focus on the wave. Like that. All right, so I'm going to draw 2 different waves. All right, so I'll draw this one and try to keep them pretty consistent in amplitude and length. And then we're going to draw a second one. We'll go with the purple marker, and we'll go like this. Okay, so let's say we've got, I don't know, microwaves up here. Where is microwave on your?
Above radio frequency.
Right above radio frequency and directly below infrared, which is directly below visible light. So we're going to call this visible light. Okay? So what we're going to find is that since everything travels at the same speed, that being the speed of light, then we can kind of make this illustration and deduce a number of different things. Frequency and wavelength, what we're looking at is microwave has the longer of the two wavelengths between visible light and microwave. Microwave's going to have a longer wavelength. All right, but if they're all traveling at the same velocity, velocity being the speed of light, then what we can do is keep our velocity constant, and this is going to take, we're going to do a couple of kind of like visual mind, game things here. Okay, not really games, but I don't know, exercises, visual exercises. Okay, so if velocity remains constant between these two, right? And I were to have something that I could push those two wavelengths, those two waves, all right? So I use this, and what you're gonna have to do is visually block what is back here, and you're going to have to, visually imagine that what's happening is as I walk that way, those two things are mashing into the end of the board. That's why I drew it all the way to the end of the board. Okay? Everybody with me so far? You're going to have to visually imagine these things just going off of the board as I push them. Okay? So I've got a longer wavelength, I've got a shorter wavelength, and I start pushing, because we're traveling all at the same speed, that being the speed of light, then if I start pushing these, they're both going to travel at the same speed, right?
Mm-hmm.
But what's happening, what's the difference aside from the wavelength, which one has more waves that are jumping off the board? The bottom one, bottom one, right? So we can say that there's a relationship between frequency and wavelength, and we've seen this relationship before. We've got direct and we've got indirect. Another word for the indirect is
Inverse.
inverse. One goes up and the other goes down, right? Inverse square law, you increase your distance, your dose goes down, right? So what can we say about frequency and wavelength then in this context? Since everything is moving at the same speed, as as wavelength goes down, then frequency goes up. Okay? So as wavelength goes up, frequency goes down. Right? Okay. Everybody good with that so far? Okay, now look back at page 58. As frequency, it's got wavelength, and it's got what else?
Energy.
Energy, right. So when you're looking at the energy, what does a negative exponent mean? Once you draw it out, or don't draw it out, but yeah, it's a decimal. And if you look at the decimals there with your energy on your, let's say your radio frequency, what does 10 to the negative 12 mean?
Very long
One was
Very, very small decimal. Right, now you look at the other end of that, and you're looking at, X-rays and gamma rays as 10 to the 10th power. What does that mean?
big number.
It's a big freaking number, right? It's a great big number. So, you look back at wavelength, and what do you see? Wavelength goes down, energy goes
It goes down, it goes up.
Yeah, it goes down, it goes up. As frequency, though, goes up, energy goes up. Right.
So they're directly.
So
related.
you want to tie frequency and energy together. Okay, so frequency and energy are directly related, directly proportional. As frequency goes up, then the energy goes up. X-rays, very, very high frequency, very, very high energy. Both of those are inversely proportional, though, to wavelength. Right. So as wavelength goes up, then energy and frequency go down. Okay. Mathematically, what we're talking about here is what we refer to as the wave equation. So you're looking at page 57. We're flipping back a page now. So the wave equation, he's got it written out here 3 different ways. I'm not going to give it to you 3 different ways. I'm going to give it to you as the very first one. That is, velocity is equal to frequency times wavelength. Again, okay, is everybody okay with this? Can I dump this? All right. I always expect this not to go quite as well as what it usually does. You know, sometimes this is as far as I plan to get in the lecture. And that's all I prepare for. And I do that and everybody's like, yeah, we got it, shut up, you know? Okay, well, then we're done.
Amy goes over it in,
And then try.
Oh, does she? Okay,
Yeah,
awesome. So it's not new to you. Okay, so the wave equation says that velocity is equal to frequency times wavelength, right? Velocity is equal to frequency, and this is what we refer to as an angstrom unit. You know, because our wavelengths can be, you know, so varied, and we've already used A for acceleration, then, you know, we're going to use angstrom unit. Okay, so I like to simplify an equation in as much as I can, you know, mathematically, just for demonstration purposes. So what's the velocity?
speed of light.
Speed of light. It's always speed of light. So, you know, I said we're going to use this one, but if you look down at the second one, what does he use in place of velocity? C. C is constant, which is, you know, Einstein's E equals mc squared is the constant. Why do you use constant? Well, because velocity is speed of light. It's constant, right? So we can substitute that. So if then the velocity never changes, it's constant, we can just assign it any number and say that's the number it's always going to be, right? Velocity is 1, velocity is 10, velocity is whatever we want to give it. We can assign it a number and say it never changes. So then we just got to deal with frequency and wavelength. So you get to the test, write this out. You know, if you can't remember what's directly proportional, what's indirectly proportional, just write out the wave equation. So frequency and wavelength, we've got 1 times 1. Is that a true statement? Yeah, it's a true statement. So what if then we were to change one of these? What would we have to do? Let's say we make this 2. Is that a true statement mathematically? No. So then what has to happen over here?
Has to change.
Has to change proportionally in the exact opposite direction, right? So 2 times 1/2 is indeed, yeah, 1. And you can go the opposite way with it and make that a 2 and that a 1/2, and you still get to the constant, the 1.
It has to.
Okay. Has to equal the constant, right? So that works for helping you to remember frequency and wavelength. It doesn't really help you to understand the correlation between frequency and energy, wavelength and energy. Just remember the frequency and energy go in the same direction, and both of those go in the opposite direction from wavelength. Okay? So again, look over that diagram on page 58. Energy, frequency go in the same direction, wavelength goes the opposite direction. Okay? Any questions on that? Okay, now it's really going to get sticky, and this is going to mess you up for the rest of the day. And not, you know, not really in a way that's going to mess you up for the test. Again, it's just an exercise. All right. So electromagnetic energy exists on a spectrum from high energy to low energy, and electromagnetic energy likes to interact with things that it can relate to, so to speak. All right. So. Anybody even listen to the radio in your car? Okay, a few people. What do you have to have in order to receive a signal on your radio?
An
An
antenna?
antenna, right. So how big's your antenna? Some of them are pretty small, right? Some of them are, maybe yay big, right? So some of them are relatively large, some of them are relatively small, okay? So radio frequency interacts with antennas that are varied in size, right? But they're relatively large compared to what X-rays interact with. And what do X-rays interact with? Electrons, exactly. Electrons, the nucleus of an atom, little bitty tiny things. So the shorter the wavelength, the smaller the thing is that it's going to interact with. Does that make sense? But also, like visible light is, it's different than any of the other electromagnetic energies in that it allows us to see. It interacts with colors. So why is white light white light? It's all of them. It's all of them together. It's all of them together. So if I took this little triangle thing? Prism, thank you. I was trying to say spectrum, and no, it's prism. If I were to take a prism and shine a flashlight through it, what do I get?
Rainbow.
Breaks it all apart and makes a rainbow. Right, right. So why do you see those rainbows? Why do you see it? Because you got the detectors in your eyes, the rods and the cones and all that kind of stuff, right? But can you see color without a prism? Yeah, so what color is that? Blue. I'm really gonna mess y'all up today. What color is that? Red.
Maroon.
Yeah, we're gonna call it red. We're gonna say it's red, but it's kind of maroon. What color is that? Orange. And this would be green. All right, so the theory behind how visible light works is that the color of the light will be absorbed in the specific wavelength and frequency of the color of the light will be absorbed in the object that is in the same color spectrum and reject everything else. Okay, let that marinate for just a second. Okay, so what that means is that red light likes red. And there's three primary colors. Yellow light likes yellow, and blue light likes blue. And it rejects everything red rejects everything that's not red. Yellow rejects everything that's not yellow. And blue rejects everything that's not blue. Okay? Everybody with me so far? Okay, so your eyes are detecting what is rejected by that color. Your eyes are detecting the light that is rejected by that color. Okay? You got me? Your eyes are detecting what that color object, your eyes are detecting the light that color object rejected. Okay? I don't like this. It's going to get worse.
So blue light likes
Buckle up. It's going to get worse. What's
So
that?
it's rejecting, so that blue is rejecting the yellow and red, and that's what we're seeing, and our cones turn it into blue? Okay.
Okay, well, we're going to stop with the cones. We're just going to go with
Is that how
that.
that works?
That's, well, no.
okay,
You're,
I was
yeah,
curious.
yeah, no. You're right, but your cones aren't turning it into blue. It is blue.
Okay.
The light you're receiving is blue because that is actually
Red,
what is not blue, which would be,
yellow.
and therefore that is
Okay, so I had it reversed.
orange.
Yeah.
Right. So what is red? Not blue and not yellow, which means that is green. That is We see orange because
It's yellow, red, so
it's
blue.
red and yellow, which means that is blue. And that is green, which is bingo, green, it's red. Right. So now you look out at the trees, and what color are the trees?
Red.
Red. You look at the grass, what color is the grass? You look at the bark on the tree, what color is that? I don't know. I don't know.
We can use that if we run a red light.
Yeah, good try. Yeah, let me know how it works out for you. All right.
See, that's actually green.
Yeah, also, that's green.
So, are you gonna see
I'm a
colors the right way
scientist.
now? Yeah. You gonna see colors right for the rest of the day? You know, you're gonna be driving home, you're gonna be looking at everything and saying, you're not what you pretend to be.
So what is white?
White's everything. White's everything.
So it's the opposite, okay.
So what is black? No, it's I'm sorry. White is nothing, black is everything.
Okay. So white
It's
is
absorbing everything.
Okay.
Yeah, yeah. So I had that backwards. Yeah.
Okay.
White is nothing, and black is everything.
And that's why when you shine a white light.
Yeah. Yeah.
You're not gonna ask us like what color something
What's
is
that?
on the test, right?
No, I'm not gonna do that. I just do this to mess with your mind.
Thank you so
It's-
much.
I'm building critical thinking here. That's what that was. All right. So that's a fun little exercise because I like to see your eyes cross. I'm mean like that. All right. So again, certain frequency and wavelength of electromagnetic radiation behave differently. I'm gonna take this off because you're gonna be staring at that. You're not gonna be listening to a word I say. So different types of electromagnetic radiation behave differently. Again, your radio frequency can carry a signal that we can reconstruct and turn into television images, to audio images, audio sounds and things like that, right? So we've got that. And then directly above that, we've got microwave, and we can heat up our food with microwave. And then directly above that, we've got infrared, which is just heat. You go into McDonald's. I don't go into McDonald's all that much anymore. I go to a drive-through, but do they still have where they, cook the burgers and then they put it under the infrared lights?
Yeah.
Yeah, okay. Okay, so what's the purpose for those lights?
Keep it warm.
Keep it warm, right. So it's heat. And directly above that, you've again got visible light followed by ultraviolet light, then X-rays and gamma rays. So from the top to the bottom, we've got ionizing radiation, and that is energy with high enough, or electromagnetic energy with a high enough amount of energy to remove an orbital electron and thereby create an ion pair. And then we get to visible light, and we get to infrared heat. Microwaves really don't play a part in what we're doing. In diagnostic imaging, you just throw it in here, and then we've got radio frequency. So what of these energies do we use in diagnostic imaging?
Ionizing radiation?
We create ionizing radiation, right? So we send electrons from cathode to anode, and I'm gonna tell you about this little move here later in the semester, but we're gonna smack those into an anode, and on the atomic level, what we're gonna get is X-ray creation, right? But before I do that, what do I create right here? Heat. We call that heat, there's two words, thermionic emission, hot ions. They're hot electrons, so we create infrared radiation right here. Now, do we want the infrared radiation? Can we create X-rays without it? No. So we got to deal with it. We don't want it, but we got to deal with it, and we deal with it like what we talked about in the last section. So we create heat here, infrared radiation. We're going to radiate it out, and then conduct it, convect it, and all that kind of stuff. We send those across the tube, but these are all hot ions. I've got to find a video. This is a little bit of a divergence. I was talking about this with sophomores yesterday. I got 3 different videos that a biomed guy was doing some work on an X-ray tube, and he actually took the took the collimator housing off, and he made some x-rays. I don't know if he was doing, output testing. I don't know what he was doing. But anyway, he took some x-rays, he took his phone, and he put it underneath and, put it on a record so that you could see what was happening whenever you made an x-ray exposure. And you couldn't really see the electrons jump, but they do, and it's like a little miniature lightning bolt. So you see lightning, what do you get? What do you see? Why do you see it?
Visible light.
It's visible light, creates visible light, right? So we create visible light here along with that heat, okay? But that's not the only place that we have visible light. You don't see that, but the jump of the electrons from cathode to anode because it's inside a protective housing, and then we've got the collimator housing underneath it. And when you get to clinicals, what you can do is look up inside, I can't draw a square, look up inside your collimator housing, and what you will not see is a light bulb. Probably won't see a light bulb. And the reason for that is because the light bulb is offset. It's over here, okay? So the filament on a light bulb is made of tungsten. What is tungsten? It's metal, right? And we mentioned this in positioning, I think, on Monday. Taking an x-ray where you forgot to lower the patient's pants, or put them in a gown, or they had a piercing, or they had a safety pin or something. What does the metal look like?
Very bright.
Very bright, very bright, right? So if the light bulb was right here, what would you see on every x-ray you created?
The light bulb filament.
Light bulb filament, right? So we don't do that. What we have, though, is a mirror, so the x-ray photons actually pass through the mirror, and for reasons we'll talk about later in the semester, the distance between here and here has to be exactly the same as the distance between here and here, not drawn to scale, but the x-rays pass through that. So since we don't see x-rays, we have to have, we're getting to a couple of points here. We have to have a way to see where the light field is going to be. So we have a light, right? Again, same kind of energy, electromagnetic energy, behaves a lot in the same way. So what do we call the spreading of the x-rays from the anode? It spreads out, we call that beam
Divergence?
divergence. Bingo, it's beam divergence. So we also have beam divergence here, right? So we've got a light field, and a field is just an interaction between energies, matter, things like that. So we have a light field that's projected that should directly match our radiation field, okay?
Is that why the distance has to be the same?
That's why the distance has to be the same. If the light was over here, then we would have a different divergence and it wouldn't be accurate.
Okay.
So the distance has to be identical, and that mirror has to be on a perfect 45-degree angle, okay? So we'll hit on that again later in the semester. Yeah. So we use light. I mean, this light up here doesn't really matter to us. It doesn't. We don't see it. We don't use it. But this light here matters a lot, right? So we use visible light so that we can see how big of an area to expose the patient to. Where else do we use visible light?
On the computer screen?
Computer screen,
Yeah.
right? It's backlit computer, well, not backlit, but LED computer screen. You get light coming off of that. So we use heat. We certainly have ionizing radiation in the form of x-rays. We have visible light. Microwaves really don't play a part, but what about radio frequency? Kind of touched on it a minute ago.
How fast the x-rays? Does it have to do with the speed of the x-rays?
Speed of the x-rays are going to be
Good.
speed of light, always speed of light. You might not have a direct connection between your computer and your image receptor, okay? Honestly, well, I do know because I was dealing with it yesterday. If you look, I think it's still there, above the sink in the lab, you'll see this thing sticking out of the wall. And that was from the previous machine, and what you'll see sticking out of that is an antenna, okay? So you make your exposure on the image receptor and it sends a signal to that, and that's hardwired into the system so that it recreates your image. And it uses radio frequency, right? Other places we're going to use radio frequency and Bushong references it is in MRI. Anybody had an MRI? A few people? Okay. So if you've not had an MRI, a lot of things about MRI. You might get a little claustrophobic. Even if you don't think you're going to get claustrophobic, you might get claustrophobic, right? Because it's a big tube, it's about a 7-foot long tube, and once you get in there, it's right here on you. Another thing about MRI is make sure that you take off anything that's metal that might be magnetic. Make sure you take it off. People die in MRI because, you know, things happen. If you've had surgery, the MRI tech needs to know that you have had surgery. They need to know what kind of metal is inside of you because it'll pull or at least heat up. If you've ever gotten metal in your eye, I told you my older son is a welder fabricator. He can be a little reckless. And he got metal fragments in his eye at one point. He can't have an MRI, most likely. He had twice. He had to go to the house ER and have those pulled out of his eye. What's that?
Twice.
Twice, yeah. So he almost amputated 3 fingers. Yeah, so anyway, I get to him. The boy almost killed me, right? So anyway, love him to death though. He's a good kid. He's just, he was my thrill seeker. He was jumping off, he was 2 or less, and he was jumping off second bunk, I mean, it's like, you're gonna wreck your growth plates, man. The legs are gonna be this long. Anyway, MRI, the way MRI works is it's very noisy. Not only is it claustrophobic, but it's very noisy. They're gonna put ear plugs in your ear. And the reason for that is because what we use in MRI is electricity to make very, very strong magnetic fields. So, and we have to have alternating current. So with alternating current, what's going to happen is inside of those coils, what will happen is because of the changing of the direction of the electrons, you get some interaction in the coils that make noise. In addition to that, what they do is that, they create this magnetic field and they put you in it, subject you to it, and then they hit your body with it's electromagnetic, it's radio frequency pulses. And without getting too deep into the physics of MRI, what happens is your body absorbs and then releases that electromagnetic energy, the radio frequency. They pick it up with an antenna, and they feed it into the computer, and the computer reconstructs, your image, the image of your body. So we use it extensively in MRI, but we do use it in diagnostic as well. If you're not hardwired into the computer system, that signal from your image receptor has to make it to your computer, and that's sent by radio frequency. So we use almost all of them. Microwave, only on break, you go heat up your lunch or whatever. But everything else we actually use, some of which we don't want to use, we don't want to have, obviously the heat we don't want to have, and we got to deal with it. Okay, so a few things on visible light, specific to visible light. What all can you do with visible light? And this is where we're going to stop. There's like 5 different things you can do with visible light. What can you see outside?
Visible.
What's that?
Visible light.
Okay, visible light, but there's stuff in between, right? There's a door, and then there's a window.
You can filter it? Would that be like filtering?
Yes. Okay. So that's not the one I was getting to, but yes, you can filter it. What filtration is attenuation. Okay, you put on sunglasses, and why is it that the light doesn't hurt your eyes as much?
It's being filtered.
It's been filtered, right? So, we had that eclipse a couple of years ago. We've had like 3 eclipses in the last few years. And you can put on dark enough glasses that you can look straight at the sun. right? And that's attenuation. You're attenuating out enough of the light that it doesn't hurt your eyes. That's attenuation. So that's one thing. What else? What if we don't have any kind of, what if, I'm gonna give it away, what if the glass on the window and the door was completely transparent? Why does the light go through it? What do we call the light going through it? It's another transmission. So we can transmit it. So we can transmit it, we can attenuate it. I never ever drink out of a straw unless maybe I'm driving down the road. Okay, so can y'all see what's happening with a straw? Okay, what happens? It's refraction, right? Anybody ever been bow fishing? If you get the opportunity, go bow fishing. It is a lot of fun. So with bow fishing, you get in a boat that's got a lot of lights and you're fishing at night because you're looking for carp or some sort of fish you don't want to eat. And what you get in this boat and a bunch of lights, and you've got like, I don't know, 2-3 seconds to draw down on this fish and let fly with an arrow before it figures out, you know, there's an alien coming after me and he swims away, right? But the thing is, you can't shoot at the fish. You can't shoot at the fish because if you shoot at the fish, you shoot over the top of the fish. So you have to shoot under the fish. Why?
Refraction.
Because of refraction. The light enters the water and it changes speed. You know, the straw didn't break, right? It's just because of the difference in speed of light as it enters that water, we've got refraction. Okay, so we've got refraction, we've got transmission, we've got attenuation. Y'all see my face over here? Oh, you can, yeah. So over here. Why?
Something blocking
Totally
it.
blocked it. Totally blocked it, right. So what did this do to the light that's coming off my great big gourd? It stopped it. It absorbed it. Right? I know I got a fat head. So I can bust on myself. So it absorbed it. So we've got attenuation, we've got refraction, we've got absorption, we've got transmission. And what did we do right here? Reflect. We can reflect. So we can do a lot of stuff with visible light, right? We can focus it and make laser beams, right? That's primarily through reflection. We can focus it. We can use focusing optics and make lasers. They'll do some really wild things. Of all those, you can't do much with x-rays. Certainly they'll transmit, right? They go through your body. They transmit, they attenuate. If they didn't attenuate, if all x-rays went through your body with the same intensity, all you'd have is a dark image. So they attenuate. Attenuation means selective absorption. You know, you pick up a pair of glasses, and what are you looking for in the glasses to make sure you don't get eye damage? Blocks 99% of what kind of light?
UV.
UV, bingo, right, okay. So, where was I going with that? You can attenuate it, block a portion of it. That's there we go. Selective attenuation, selective absorption is what attenuation is, okay? So you pass a beam of radiation through the patient and you've got absorption in bone, high absorption in bone, less absorption in soft tissue, even less absorption in like, you know, air, right? So let's say you want to increase the absorption in all those tissues. What controls your penetration?
KVP.
KVP. So what would you do with KVP? Lower it. If increased KVP increases transmission, then decreasing KVP decreases transmission. Right. Okay, so you can attenuate it, you can transmit it, you can block it, right? So you can totally absorb it. If you try to x-ray through just a jug of barium, you don't get much with barium. but you cannot refract it. Okay, and I'm going to offer a caveat here. If you dig deep enough into the internet, there is evidence that X-rays can be minimally refracted. Okay, but for testing purposes, I'm going to say you cannot refract it. Okay, for registry purposes, it's not refractable. Okay, so go with that. You can absorb it, you can attenuate it, you can transmit it, you can't reflect it, you can't bounce it off, you can't focus it. And that's a point that you're going to struggle with a little bit. You can't focus X-rays. So what are you doing when you collimate? You're just blocking it. That's all you're doing, is you're restricting the beam. You're not focusing it. And where you're going to kind of draw an inaccurate correlation is you're focusing on the anatomy of interest. Okay? But that's not focusing the X-ray beam. So if you shoot a KUB, you're looking at the entire abdomen and you see the L-spine through it, right? So if you collimate down to just the L-spine, you're just blocking a portion of the abdomen. You're not focusing the X-ray beam on the L-spine. You're focusing your eyes on the L-spine. You see the difference between the two? You cannot focus an X-ray beam.
Are the plates that block red tungsten?
Lead.
Lead?
Yeah, yeah. Okay, we're good with all this? Any questions? I love the look sometimes. Want me to draw the dots back up here? No. Yeah, I knew it. Yeah, you're gonna be thinking about it all day. It's like if I tell you, okay, everybody hold your breath for 2 seconds. You're not gonna breathe right the rest of the day. That's 2 things I got you on. All right, any questions? Yeah, how many of you want to flip me off right now? All right, I'm done with you then. Y'all have a good one.